just want to go back one slide and just make a comment. When we're talking about that we're defining these registers, when we talk about the LFSR logic, the custom logic, and the register definitions, this is an example of what a user might do. So it's not us as Alorium that's defining these, it's whoever's writing this custom logic. They would also define these registers for themselves as far as what the functionality of those registers are, how many there are, what addresses they go out. That's all something that the user does, and they're able to do anything they want there. So now let's look at the wrapper module itself. As I said earlier, this module is intended to add an interface to the configuration register data bus. So we'll be renaming it now to Accelerate LFSR and then instantiating our module in there. And I'll just go look at the code itself here by bringing up Quartus. So you can see right at the top here, we've defined a couple of parameters, 3 parameters that hold the values for our address. They default to 0, but when we instantiate this, we'll specify something else there. And then in our input-output list here, you can see most of these are our standard data bus signals for the configuration data bus, which by shorthand we just call the D-bus. There's also the some signals for what we're defining for LFSR here. Just going to scroll down just a little bit here. Not sure how that translates on the webinar, but this logic here is somewhat boilerplate. For each of the configuration registers, there's 3 of these equations. We create a select, a write enable, and a read enable signal for each of those registers using the standard logic here. And each of those has its own parameter, the control address here, the seed address here, the data address here, that correspond to the registers that we're talking about. Next, we need to, on the output side, creating the data bus going out and the output enable signal that goes with it, we need to combine together the data coming from the 3 different registers. That's what's happening here. And then for each of the registers, the configuration registers, we have a little bit of control logic. For instance, for LFSR control register, we have this logic, which on a reset clears the register, all zeros. But otherwise, if we're not in reset, then whenever we have a control write enable signal, we parallel load the LFSR control register from the D-bus input. There's similar logic here for the LFSR seed, where it gets cleared on reset and loaded when we have a seed write enable. And we're also loading the seed write enable into another register that we're calling the new seed. That's not a configuration register, it's just a holding register so that we can line up the data in LFSR seed register with the write enable signal that's going to go into our instantiation. Scrolling a little bit more now here, we can see the instantiation of our custom logic right here and the assignment of signals into it. And we can see that we're using bit 0 of the control register going into the enable input, and we're using bit 1 of the control register going into our long_HB input. We can see our outputs, our heartbeat signal coming out, and LFSR data coming out. That's actually also one of our configuration registers. So in this case, a configuration register is actually living inside of our custom logic, but it's still addressable via the configuration data bus. Let's go back to our presentation now. So now, having wrapped our logic in the wrapper template, we're going to instantiate it in the OpenXLR8.v file. Now, as I mentioned earlier, the OpenXLR8.v file is the top level module, and it gets instantiated at the top level of the FPGA logic and communicates directly with the AVR core, with the input and output pins, with the interrupt logic. it provides access to all of that stuff to the user's logic that lives inside of the OpenXLR8 module. So you can communicate with the input and output pins and interrupts and the core itself. I'm going to bring up Quartus again now to look at the actual code for that. The OpenXLR8.v is a little bit longer file, and that's mostly because we've added many, many comments to make the file self-documenting. So don't get too intimidated by the length of the file here. Most of it is just comments. I call it the wall of green because comments are green. Here in the header, we can see that there's basically 6 sections of this file that contain the various pieces that we are concerned with. The first section is going to define our input parameters and input and output signals. Here we're actually including a file that defines those. We store that over in XLR8 core so that we can easily update that if we decide we're going to add a new signal to the OpenXLR8 module without having to go out and modify every existing OpenXLR8 implementation. But we do in the comments here have a copy of the current contents of that file for reference. And you can see parameters being defined here at the top. We got our design config, which is used during compilation to specify what type of image we're building, since there are different size FPGAs and there are different boards that have different features. We've got the num pins, which tells us how many pins we have on our board that we'll be able to access. For the UNO board or for the XLR8 board, it's 20. It's more for the snow or the hinge. And then we've got some other parameters that allow us to communicate with our interrupt logic within here. Here's the inputs and outputs to the module itself. We've got clock and reset as normal. We've got a number of different clocks that are available for the user logic so that you don't have to run at the core clock rate that the rest of the FPGA is running at. You can use faster clocks. We provide the 16, 32, and 64 megahertz clocks as standard. And there's also a couple of optional clocks where the user can specify those clock rates and then use them within their own logic here. So you can run the OpenXLR8 modules at faster clock rates than the rest of the FPGA. The enable clocks here, really these are more like heartbeat signals that are used for timers, kind of giving you a little bit longer duration heartbeat signals. These signals here are the standard data bus, D-bus interface signals coming into OpenXLR8. The other section here contains the GPRF, which is actually a copy of the AVR register file in its entirety. So that's available for the OpenXLR8 users to read values directly out of the register file. So rather than having to use an I/O operation to transfer a value from the register file out to the OpenXLR8, the modules in OpenXLR8 can read those directly. There is no write access though to that, it's just read. XB pin X is a copy of the values of the input pins. This is how the OpenXLR8 modules read values off of the pins. And then these JT signals are the JTAG pins on the board. These pins are not normally used during normal operations, so we make them available for OpenXLR8 users if they want to use them for something else. These next 4 buses are used for controlling the output pins, and we'll get into the details of that in a bit. And the final one here is our interrupt signal going back to the core. Scrolling a little bit here. This next section is where we define our signals that we use within the module. Again, here's some that are used for controlling outputs, and those are standard and don't need to be modified by users. We'll get to that in a second. And then for signals that are unique to whatever implementation of OpenXLR8 we have, we would define those here. Here you can see we've defined a couple of signals for our LFSR implementation. Scrolling again, and here's our implementation or our instantiation of the LFSR wrapped module. And you can see we're feeding in at this point the addresses that we're going to use within there. So you might recall we set those to default value of 0 in the actual wrapper, but here we're feeding in the values we'll actually use. And the signals going in and out of the LFSR are mostly the standard D-bus, but you can see we are also feeding in these heartbeat signals, and we've got some outputs for like the D-bus out and whatnot. So now we get to our output control. This is a little bit more complicated than one might think. The reason for that is that we're following the standard that's defined in the AVR architecture spec. In that spec, they use 4 different signals to control each output pin. Essentially, there's 2 that are called the DD signals. Those control whether we're going to actually be controlling that pin, and if so, how we're controlling it. So the DDOE signal here is used to say whether we're going to control the pin or not. If we set that to a 1, that means that this signal is going to control that output. And then we can use the DDOV signal to determine whether that pin is going to be an input or an output. If it's a 0, it's an input. If we set it to a 1, it's an output. In the case where we set it to be an input, the other 2 signals don't really matter, they're ignored. But if we set DDOV to a 1 and we're using it as an output, then at that point the PV signals come into play. PVOE is used now to turn on that output. The output enable signal controls whether it's actually active or not. And if it is active, then the PVOV signal will specify the value that goes on that pin. So now if I scroll down a little bit more here, you can see in these assignments that we're specifying values for pin 2 and pin 13. In the case of pin 2, that is going to be an input, and it's going to be a signal that eventually will control pin 13. But since it's an input and we want to control it, we're going to set DDOE to a 1, saying we want to control this pin, and then we're going to set DDOV to a 0, indicating that it should be an input. For pin 13, we want that to be an output. Pin 13 actually controls the LED on the board. So we want it to be an output, so we say, yes, we want to control it, so we set DDOE to a 1. We want it to be an output, so we set DDOV to a 1. Then we're going to use the output enable of that and use the actual input signal on pin 2 to control the output enable of pin 13. So if pin 2 is a 0, then the output will be enabled in this case. And if it is enabled, then we're going to put our LFSR heartbeat signal onto that output. So as I said, it's a little more complex, I think, but it provides ultimate control over those outputs.
And as you said, Steve, this is basically all because we wanted to maintain, compatibility with the AVR architecture, right? We're just following along those lines.
Exactly. You can look this up in the AVR architecture spec, and it lays out these signals just as I've described them. Scrolling down a little bit more here. Here we have some standard logic that, as it says, do not edit below these lines. This is in the case when you have multiple modules instantiated within the OpenXLR8. Perhaps you have different blocks that are communicating with each other and using different pins. We need to combine their control into a single bus on the way out, and that's what this logic does. A little bit further down, for the output related to the D-bus, we need to combine outputs of multiple blocks if they exist. In our case, we only have one block, the LFSR, so we just use the LFSR D-bus out and the output enable directly. If we had more, as you can see directly above here, this is the case where if you had 3 different modules, you would have 3 different D-bus outs and 3 different enables, and we just combine them as shown there. And the final section is for inputs. Our LFSR example does not use any interrupts, so we just set that value to a 0. But if you did need to use interrupts, we have a module that we include It's called the XLR8 PC int, and that provides the interface that we need to the interrupt logic of the AVR core itself.
And Steve, one of the things that I was going to share at the end as well is that we've got some plans for some upcoming webinars in addition to this one. This is the intro level, but we also are going to be doing sort of an advanced OpenXLR8 down the road, right? Where some of the things we're going to talk about there would include things like if we're going to use interrupts, how do you use that? How do you use our interrupt block? How do you maybe stitch together multiple XBs? And we would cover that kind of material in that advanced OpenXLR8 webinar. Is that correct?
Yep. Yeah, we just don't have time in the scope of this workshop to do that.
Right. Understood.
We'll cover these things in other videos.
Great. Yep. I just want everybody to know that we do want people to understand that we're going to be putting some additional content together as we get into more complexity of how you might want to stitch things together. We do plan on doing some subsequent webinars that get into that level of detail as well.
Yep, absolutely. So now we've got all of our source code modified and put together. Now we're going to modify our XB address pack file to specify those register addresses that we've been talking about. So this address pack allows us to define values for some parameters that are used then in the logic. So these 3 lines here, where's my cursor? There we go. These 3 lines here, these names should look familiar. We just saw those in the code a minute ago. And now we're assigning values, in this case, E0, E1, and E2 as addresses for those registers. This file also is kind of a wall of green. There's a lot of comments. We can't show them all here because there's so many, but basically for all the available address space, we list which addresses are available for use in OpenXLR8 and which are not. There are some addresses that are used by the AVR core. There are some that are used by Snow or Hinge in those cases, since they have additional features beyond what the standard AVR does. And so in those cases, they use some additional addresses. But it just indicates in there which addresses you can use and not use. There are many, many addresses available, so no one should have a problem running out of addresses. So now we're done over in our RTL directory. We're going to go over to the Quartus directory now and modify the OpenXLR8.qsf file. So the OpenXLR8.qsf file is a Quartus settings file, and it allows the user to set any Quartus settings that they would want to do for their design. Mostly what that consists of, as shown here, is a couple of statements that just tell Quartus where to find our custom logic source files. The Alorium LFSR.v and XLR8 LFSR.v. Those are the new ones that we created. The OpenXLR8.v, for instance, the other scripts already know all about that, so you don't have to specify that. You just have to specify the ones that are newly created for this particular OpenXLR8 implementation. So now we've got all our files modified, and we're now ready to launch Quartus and actually start building something.